Thank you so much. Hi, everybody. So as introduced, I'm CEO at Ivy, and we're trying to take on quite an ambitious mission to unify all machine learning frameworks. Not an easy feat, and something we're having a lot of fun trying to do. Again, slightly a maybe kind of provocative sentence there, unifying ML with one line of code. Um, and I'll throughout the course of this talk, explain how by using the functional API of machine learning frameworks as an intermediary, we actually can get machine learning frameworks running together interchangeably with only really needing users to worry about adding one line of code to make this work. So a slightly kind of dramatic sentence, but hopefully seems somewhat justified as we go through. Um, Okay, so so what Ivy predominantly aims to do is be a zero code solution to make all machine learning frameworks interchangeably work together. So that means take a function from TensorFlow, maybe in this case run it with, well, in Ivy in this case, but you could also run it in a JAX pipeline, set the backend to be whatever you want, and then use whatever hardware is available to your backend. So the main goal of Ivy is to enable people to mix and match any of the code that's out there without them needing to worry about kind of different versions and different frameworks preventing things from operating together. And this is kind of a broad outline of the sections with some nice emojis there as well. So this is broadly kind of what we'll be going through today. I'll first go through Ivy in a pretty quick rundown of the main points. Then I'll talk a little bit about the machine learning stack and how Ivy fits into that and how it kind of complements a lot of the great unification work that's already been done. Then go a little bit deeper into Ivy's design, and then talk about Ivy as a framework, Ivy as a transpiler, which is these two kind of slightly different ways that you can use Ivy. And then we'll also talk about how in the future we see Ivy potentially becoming this kind of universal docking station, and also then give thanks to the team for their hard work as well. Okay, so let's dive in. So first question, what does Ivy do? That's a pretty good place to start. You'll have to excuse the graphic design here, something that maybe I should get a professional at some point. Basically, the state of ML at the moment is that there are many great tools out there, but once you've chosen a framework, you're limited to their specific tools and ecosystem within that framework. This needlessly closes the door on many useful tools. So if you're using PyTorch, there's a very strong ecosystem, and you also have very good third-party libraries, whereas with JAX, you have all of the state-of-the-art models from DeepMind, and it's very high performance on TPUs. TensorFlow, very kind of established in industry, very good edge and mobile bindings via TensorFlow Lite, for example. So they all have their own strengths and weaknesses, and but at the moment, you kind of need to lock yourself into one of them. Whereas with Ivy, you don't need to do that. You can kind of have no horse that you've backed, and you effectively can just kind of float between them. Okay, so for example, so if a great kind of state-of-the-art model, hot off the press, arrives on the scene, what happens at the moment is that a slew of open source developers do great work in re-implementing this model in all kinds of different frameworks. This is a good thing, but it does inevitably lead to a lot of issues and a lot of pull requests because the devil is very much in the detail in ML, and slightly different kind of initializers or small differences can lead to quite big differences in training. And this can be very, very hard to debug because you're not getting errors, you're just getting a training curve that isn't converging correctly or something. So a lot of issues, a lot of time, and a lot of people spent just trying to recreate the original. Whereas with Ivy, this is kind of the one line of code. Ivy enables you to transpile the, in this case, Haiku model into a Torch module just with one line of code, and then you can train your Torch module with a Torch optimizer, for example. And we'll go into a lot more detail as we go through, but again, this is just kind of an introductory overview of what Ivy can do. Okay, so on top of Ivy being a transpiler between frameworks, it is also a fully fledged machine learning framework itself. And as a kind of demonstration of what can be done, we've also added some of our own libraries written purely in Ivy. So rather than just converting what already exists, you can also write your library or your models in Ivy directly, and then this will be back-end agnostic, and you can then run your library or your models anywhere without needing to kind of transpile the code. And again, just a quick example of this, for example, in Ivy Vision, this slide really just showing that Ivy is complementary. The intention is certainly not that now everybody writes everything in Ivy. The intention entirely is that you can use Ivy functions in the code that you already have written in whatever framework you're using. So here we just have one line where there's a vision function in a TensorFlow model, for example. And again, we have here a visual example just showing that you can do quite interesting things with the Ivy libraries that already exist. I won't go into the details because again, it's not necessary, but you can see kind of sample spline path, converting a vector pose to a matrix pose, doing sign distance functions and so on. And actually this particular example, there's just kind of a, we just did some some gradient-based motion planning of a drone and of a manipulator. And all of this is with pure Ivy functions and just a bit of a taster of what you can do with the robot library, for example. But the focus isn't on the libraries. This is more just kind of showing what Ivy as a framework can do with some example libraries. Okay, so this is what Ivy does. So now let's touch on to, again, in a nutshell, relatively high level, how does it work? So the first point to make is that Ivy has, first of all, these framework-specific backends, which are implementations of Ivy's unified functional API. So in this case, it's very simple because it's purely syntactic. We just have a different function name, basically. Ivy clip versus clip by value, clamp, etc. But the point here is that we have one function which has unified syntax and call signature, and we implemented this function using various backends as a composition of the backend functions that already exist. And in general, this might be one or two functions. It doesn't just have to be one, but in this case, we've chosen a simple one so we can fit it all onto the screen. And then what we also do, importantly, is we re-implement the functional API of each framework on top of Ivy. And these are what we refer to as the framework-specific front ends. And all of this is done as a composition of Ivy functions. So for example, we recreate the whole TensorFlow functional API using Ivy as kind of the building blocks for creating this. And then effectively, Ivy acts as the intermediate representation between these frameworks, which enables us to arbitrarily mix and match any front end and any back end. So we take TensorFlow code and add it to a PyTorch project here, for example. And again, this scales kind of linearly with the number of frameworks that we support rather than quadratically, because we don't kind of directly bind each front end to each back end. We only bind them to the intermediate representation. So kind of very much compiler 101. And then again, from a relatively high level, so this kind of broadly explained how Ivy works as a transpiler. With regards to how Ivy works as a framework, basically what this slide demonstrates is that we only wrap the functional APIs of the frameworks. We don't wrap the high-level classes. And this makes Ivy very scalable to changes in the frameworks, because generally speaking, the frameworks have very strong forwards and backwards compatibility requirements. A lot depends on them, not least their own high-level classes, but also third-party libraries. So generally speaking, when we implement Ivy and it supports Torch version x.y, it will then also support x.y+1, because it's in the interest to have very strong forwards compatibility, and the frameworks do a good job of that in general. So the point being that it's not kind of like every new version is a huge explosion of work for Ivy. And also the important point is that there's all these kind of reinvented wheels, I suppose, where there's these high-level optimizers and trainers and so on, and layers, and Ivy just does all of these once. It doesn't kind of try to wrap them lots of times. It only wraps its own functional API, which itself does the wrapping, which makes it, again, a scalable design. So that's a broad overview of what kind of Ivy can do, how it works on a high level. But I think that the story is definitely incomplete without giving consideration to all of the other unifying efforts that have occurred in the ML space, and kind of really putting Ivy in the context of all of that, I think, is important. It's certainly not the first attempt to provide unification in some form, and I think Ivy is very complementary to the efforts that have already been done and are ongoing, and I think it's useful to kind of put that into context. So we'll now talk a little bit about the ML stack today, represented here very nicely with a pancake stack. So we'll start off with framework explosion, which is basically slightly dramatized, but giving a sense of kind of how many frameworks have kind of come onto the scene in the relatively recent past. So this graphic shows not all, it's certainly not exhaustive, but relatively exhaustive with some of the major kind of array processing frameworks. I wouldn't necessarily limit it to machine learning, but kind of matrix-oriented frameworks, let's say, or tensor-oriented frameworks. So, I mean, there's MATLAB, the SciPy, Torch, NumPy, scikit-learn. I could list them all, and I don't think it's necessary to go into details of the whole history of kind of where these things have come about and what the benefits are. I think it might be useful to kind of explain a bit about the fact that, generally speaking, each framework has come in onto the scene and brought something to the table that has meant it's, which has enabled adoption because it adds something that wasn't there before. TensorFlow, kind of in the context of Caffe and maybe Chain at a similar time, but definitely the Python interface was much easier than Caffe to kind of quickly prototype things. Although the lack of eager execution and the fact that there was a static graph made things quite hard to debug because you had to enter into the session in order to kind of see intermediate variables. This enabled PyTorch to quickly come on with its fully asynchronous distribution on the GPU with pre-compiled kernels, and a very Pythonic design meant it was able to kind of find its place with TensorFlow already having predated it. And JAX, for example, again, I'm kind of simplifying a bit here, but JAX, with it being fully functional, having very powerful gradient computation, which means you can compute Hessians and Jacobians and things like this very elegantly, very high performance with it sitting very closely above XLA, which is very highly optimized for TPUs, means that has its own place for kind of high performance computing and also more bespoke gradient handling, for example, and also the VMAP, where you can kind of parallelize things in a more elegant way, and PMAP as well. And then also actually Dex language as well is got some interesting things built on Haskell. But basically, the point here being that there's a lot going on, and I don't think, although PyTorch is perhaps, I mean, I won't. I think in research, PyTorch is the front runner probably. I know that TensorFlow is very useful and is used heavily in industry, and JAX obviously in DeepMind and Google. But I think that's not the phrases. I think it's still unclear that there's one framework to kind of dominate them all, and I think we're still going to see much more interesting developments in the space. So what does Ivy add? Well, I think before answering that, it's useful to kind of think about the stack. And again, talking from a relatively high level, and also I would emphasize here that if anybody has better knowledge than me on how I've constructed this ML stack, then please send me a message or ask questions at the end, because it might be that I'm missing something, but this is kind of how I've constructed the hierarchy as it will unfold. So the first thing, well, I've put at the top is kind of standards, because these don't have an implementation. I think the array API standard I've put at the top of the stack, at least in Python, because it's kind of saying what the API should be at the user-facing level, basically, without kind of implementing it, but saying this is kind of what a set of norms is that we can all kind of work towards. So I've put that at the top. Then I would say there are the kind of the wrapper frameworks. So Tensorly had, and does still have, I should say, various backends, kind of JAX, TensorFlow, PyTorch, etc. Think, again, does, EagerPy does as well, Neuropod from Uber does to some extent, and Keras did, but now is focused on TensorFlow. And yeah, so that's those. And I think really we put, well, first of all, we say that these are all unifying, they're kind of striving to unify. And I would very much kind of put Ivy with these. I kind of put it with Array API standards because we are adhering to the Array API standard and are kind of extending beyond the functions there quite a lot, and perhaps would ideally like that to also form part of a standard. So therefore kind of bridging the gap a little bit. And importantly, there are some key differences that Ivy has to these particular pieces of work, which I'll go through now before then going further down the stack. Yeah, I mean, the first point is that Ivy is also stateful aside from being just functional. And for example, Tensely and EagerPy are much more focused on the functional abstraction, so kind of keeping things at the kind of mapmul, add, expand dims, etc., but not kind of having stateful trainable modules and layers and optimizers and so on. So that's kind of one initial difference. On the other hand, Think is more focused on the stateful slightly. It does have a functional API, but it's kind of not exhaustive, and it's a bit more kind of about composing neural networks with any backend very simply and easily. And Europod is kind of even higher level still, and is more about interfacing kind of inference of different machine learning frameworks and kind of maybe running these together through a unified API, but kind of really on the top of models rather than kind of going right down to the APIs. And Keras is perhaps one of the most similar, but of course now is deprecated as far as a unifying engine goes. So these are some differences, but actually I think the main difference, I mean, these are all, I think, relevant differences, but I think the main difference is that Ivy has the front-end API. So Ivy isn't just trying to be a wrapper framework, it's a wrapper framework and a transpiler. And I think that is the most important difference to other important pieces of work that have inspired Ivy. Okay, so then I think next we have the frameworks. And again, I'm not limiting to Python here, I'm kind of including everything. So yeah, we have Apache Spark, we have Flux with Julia, and I've kind of got a few other things in there as well, in C++, and in Lua, etc. And again, Ivy clearly is different to these because Ivy is trying to unify these. So yeah, so quite a clear kind of answer to what Ivy's adding in that regard. Then I kind of see the graph tracers. Again, these aren't with every framework, but I think they're quite important. I think TorchFX is actually a very important piece of work. We go into detail on all of this in our documentation, so please feel free to kind of dive into that. But again, this is kind of what I would then see being one level below. And then kind of, I think, again, a really another relevant kind of set of tools are neural network exchange formats. I put kind of Apple's ML tool in here, which I think is maybe slightly pushing the boundaries of what an exchange format is, but that's just because they can load in an intermediate representation from TensorFlow and PyTorch for then running things on Apple devices, so not quite. But these two certainly are exchange formats. And again, I think the big difference with Ivy, again, kind of really just framing this all in kind of what does Ivy add? So these are kind of static file formats, which basically, I suppose if a framework wants to be able to convert to this format, the authors of this framework to some extent kind of have to buy in, because the ONNX, for example, says this is what the standard format is, and then people can kind of opt in to be able to convert to this format. So the first difference is that Ivy doesn't require buy-in. We kind of do all of the work for the third-party frameworks. We kind of wrap their functional APIs so that they don't need to do anything at all, and Ivy can support them. So in that sense, it's less work required for third-party libraries. And the other point is that ONNX is much more focused on deployment. Again, a really important problem, which is why I think it's complementary. But it's very much about kind of, you've trained a model, now you write it to a standardized file format, this kind of intermediate representation upon which hardware then understands it, and you can then run it highly efficiently on various devices. And kind of, there doesn't need to be all these different representations. So it's solving a slightly different problem. It's solving the kind of deployment fragmentation problem, whereas Ivy kind of goes a step higher up the stack and says, well, let's also kind of solve the training fragmentation problem. So you can throw code together in your Python console and train it kind of end to end. Okay, and then we have compiler infrastructure. Obviously LLVM, MLIR, really important. And actually I've put modular here as well, a new, from the creators of MLIR that's doing really important unification work as well. More compiler infrastructure, not my deep expertise, but I know so much just to say that kind of writing the protocols and the infrastructure that enables people to write compilers in a kind of standardized, unified way, and kind of helping to solve the noisy fragmentation that that exists in the kind of compiler space. Then there's kind of multi-vendor compiler frameworks. Again, I kind of bunched a few together that aren't exactly the same, but an XLA, I think you could question whether it would be a multi-vendor compiler framework, though it does compile to kind of CPU and GPU and everything, obviously. But basically, Apache TVM is a clear one, and OctoML, of course, again, extending from that, where the problem is kind of, can we just make sure that we can take a model and run it on any hardware and solve that elegantly with kind of useful abstractions to unify the fragmented low level, which we then get into now with kind of vendor-specific APIs and vendor-specific compilers. And again, we kind of very quickly get to fragmented space again. So there's a lot of useful work. In a nutshell, there's a lot of useful work trying to unify kind of the fragmented landscape down here, which I think is really important and is not what Ivy is doing. It's kind of assuming that this is solved. and Ivy is kind of actually trying to unify the APIs that users interface with when creating code so that people can share at this level as well. So it's kind of unifying a bit higher up the stack. And again, being not only a framework, a new kind of extra competing standard, it's adhering to the standard, and it's an intermediate representation enabling transpilation. So you don't need to write any Ivy code in order for it to benefit. Okay, so that's kind of how Ivy sits in the whole context of the ML landscape. And again, yeah, the bottom is fragmented here as well. Okay, so I shall have a quick sip of coffee. Okay, so now onto the Ivy design. Also, I'm not sure how questions work, but I would also like to say that questions are completely welcome. So people are welcome to stop me midway through. I assume that everybody is able to interact with the Q&A section on Zoom. I'm not super familiar with this interface, but if anybody does have questions, then please feel free to ask at any point, and we can kind of keep it quite discussional. But otherwise, I'll keep plowing on, and we can have questions at the end. Okay, cool. So I'll keep going. Okay, so so we're now on to there you go, Ivy design. So we've actually already looked at this image, but what I'm now going to do is kind of show how there are parts of Ivy which adhere, that kind of form building blocks both for Ivy the framework and also Ivy the transpiler. And there are also parts of Ivy which are unique to kind of one of these goals. So we earlier on saw the backend API, Ivy functional API, and the framework-specific front ends. So I'll put that down here and convert these to these kind of three blocks. So this is now what these are representing. We also have a backend handler. I won't go into the details. There's another lecture actually where I go into a lot more detail in each of these, but we will kind of won't go crazy deep in this session on that. So this is kind of these building blocks. You can already see some colors different that I'll explain in a moment. We then had this slide earlier as well, where we showed that Ivy has its own functional API and its stateful API, and we kind of disregard these quotation reinvented wheels. So again, kind of how this fits into the block diagram we're building. Well, first of all, these aren't part of Ivy. These are kind of the backend APIs. This is the Ivy API, and then we have the stateful API, which is kind of where we have the as I say, the module, the optimizers, the layers, and so on. So this is kind of the stateful API and also this container. I won't go into the details of that today, but again, it's mentioned in an earlier lecture. So that's kind of this. And then the final piece of the puzzle is Ivy's compiler. This is actually a dependency graph, maybe a bit unintuitively, but it's actually going from code to the graph, but the graph depends on the compiler, which depends on the code. And this is kind of, again, one of the building blocks. So with regards to what these mean, we basically have the building blocks in orange. So these are useful and necessary for both Ivy as a transpiler and also Ivy as a framework. So kind of integral to both. Then the front ends, hopefully quite intuitively, are necessary for the transpilation process. As we kind of showed before, we can then take TensorFlow code and convert it to PyTorch code using the TensorFlow front end. So that's really not about Ivy as a framework, but really about the transpiler. And then again, Ivy as a framework, the stateful API, the containers, these things that are all about composing high-level modules, are not about transpiling at all. They're just about making Ivy a useful framework. So hopefully this kind of somewhat simplified image gives you a relatively clear overview of how Ivy is fulfilling these two quite distinct end goals with a lot of shared kind of work and a lot of shared building blocks. Okay. I think it's worth going into a little bit of detail about the compiler, because this is actually a very important integral part for a lot of the stuff we're going to be discussing today. So I'm going to quickly, I didn't bring it into the deck in time, but I'm going to quickly link to here. To basically just explain briefly what the graph compiler does. In words, basically the graph compiler takes any code kind of written in Python, and it extracts the computation graph as a composition of the backend functions in the functional API. So in this case, whether we have Ivy code, which is wrapping Torch, for example, in the backend, or whether it's pure Torch itself in the function that we're compiling, or a mix of Ivy and Torch, for example, all of these will compile to the same computation graph, because under the hood we're compiling to Torch and it's just Torch functions being juggled around. So kind of Ivy is unwrapped from the Torch, for example. Likewise, if we have a network and we want to compile the forward pass of the network, whether we've kind of defined a stateful layer in Ivy, whether it's a super simple minimal kind of linear layer operation, or whether it's an unclean one with redundant bits of code that don't connect the inputs to the outputs of the function, with printed messages, temporary variables that don't end up being used, all of these will compile to the exact same graph, because we're only concerned with the input to output graph of a function, which stitches together the functions in the functional API. There's actually some similarity to some extent with Torch FX, which is a piece of work you should also check out. But the difference here with Ivy is that this is framework agnostic, and this works for NumPy, JAX, MXNet, TensorFlow, and Torch, using the same kind of technology, the same compiler logic. Okay, so that's kind of the graph compiler in a nutshell. Okay, so that's kind of, again, Ivy's design and how we're kind of solving these two quite different problems with the same fundamental building blocks. So I'll now talk about Ivy as a framework, but we won't talk about this for too long. I'll kind of go through this relatively quickly, and then we'll dive quite a lot deeper into Ivy as a transpiler, in keeping with the title of this talk, kind of Unifying ML with one line of code. Again, a slightly dramatic title, but it's much more related to the transpiler entirely, because this is where we can kind of add a single decorator and convert entire modules and entire libraries to new frameworks. But we'll also talk about Ivy as a framework a bit as well. I think the most important part of Ivy as a framework is the module. So we can construct neural networks in Ivy, which then have an arbitrary settable backend. And basically, there's quite a lot going on if you actually look at the source code, but probably the three clearest overridable functions are create variables, build, and forward. And and create, well, build is basically for building or child modules. So if you have like a linear layer, you'll do like self.linear equals ivy.linear, etc. Creating variables is about creating variables that are not present in the child modules, that are kind of very much unique to this module. And then the forward pass is defining the forward pass of the module, which is the class that's used either for layers or for whole networks, very similar to kind of torch module uses, really. And I don't think we need to go through all of these. I think maybe I'll show linear and also multi-head attention, because I think they're slightly more interesting ones. Well, kind of linear is quite simple and multi-head attention is a bit more interesting. So quickly showing linear. Basically, I mean, we have a lot of initialization. We define an initializer for the weights, an initializer for the bias, a few flags, device, data type. We can specify all of the trainable variables up front, channels, etc. We just define these in the constructor. Everything in create variables. So we define this kind of dictionary. So it should return a dictionary, V, and we have the weights, W, the bias, B in the dictionary. We use the initializers to construct them and return it there. And the forward pass defers entirely to the functional linear function. And in fact, the design of Ivy Stateful API is very much that we build on top of functional functions where possible. So we have a multi-head attention function and an LSTM update function, just to kind of maximize the abstraction. Okay, so that's the linear layer. I can quickly show this. It won't take too long, actually. I think this is pretty good. Give you a good sense of what Ivy as a framework looks like. Again, we have initializers, various other configurations. Again, we create the variables, the weight and the bias, and then the forward pass, again, is entirely a functional wrapping. So again, very lightweight layer implementation with the functional version doing all the heavy lifting. And I believe it's the same for LSTM as well. Yeah, we have this get initial state helper, a bit more complicated because we have kind of recurrent weights and various layers and so on. And we do a bit more here because obviously we have to kind of unroll the LSTM. So we do kind of the LSTM update function multiple times and kind of update all the states and so on, because we want to be able to perform a fully unrolled LSTM as forward pass. But again, kind of wrapping quite heavily a functional version. And finally, I mean, I might as well go through them all just to really give an overview. No need to understand the crazy details. Well, this is a bit interesting because we actually do create the variables. Oh, no, sorry. In this case, we build as well, because the multi-head attention has optional kind of linear layers, mappings to the queries and the keys and the values, which form part of the module. So in a way, the multi-head attention behaves a bit more like a mini network with its own child modules, which is why we then use the build in this case and not just the create variables. But we also actually override the convention of some of these variables just to give it a new name, basically. But yeah, basically the point here that this is a bit more complicated, and we actually do build child modules as well into this slightly more kind of compositional multi-head attention module. But basically, kind of you override these three. You don't need to override build. If you don't need to build anything, you see with the linear conv and LSTM that we just ignored this. You also don't need to create variables. Actually, some activation functions, if you want to treat it as a layer, you can leave both of these out, and the only one you need is the forward to be actually implemented. So it's very easy to kind of define your own layers and compose them together. And then for a more interesting example, so I'm not sure how many people in the audience are fans of transformers, but I'm certainly a big fan of Perceiver.io, a DeepMind architecture that showed really impressive application to high dimensional inputs and to high dimensional outputs. So it was able to, for example, get state-of-the-art performance on optical flow, which is really impressive for a non-kind of hand-designed architecture. Up until that point, things had to be kind of much more handcrafted. Anyway, a very cool architecture. And basically, yeah, we've implemented this in Ivy. And you can get a bit of a sense of what this looks like. We build everything. We have kind of cross-attention layers, latent attention, the layers specified here. We create some custom variables that aren't part of the child modules, such as the latents and the decoder queries, and then a relatively lightweight forward pass. So kind of in 200 lines of code or so, we have it all implemented in Ivy. And what this serves to do, more than just kind of quickly showing you a transformer architecture without you really being able to take it in, most importantly, this has helped us to answer a question, which is, to what extent does the Ivy abstraction kind of maintain numerical stability, for example? At the level we're abstracting, we're not guaranteeing identical operations at the level of bits, for example. We're just kind of abstracting functional APIs which themselves can do whatever they want on whatever hardware using whatever low-level compilers that they're designed to use. And all we're kind of doing is making sure that the maths basically kind of aligns. So of course we're going to get rounding errors and we're going to get kind of numerical differences slightly with kind of each of the backends in Ivy. But what we've been able to show, again, actually this is just showing that we can compile the graph. A quick aside, which is what we do when running efficient inference in any Ivy module, to kind of compile the forward pass and unwrap all of the Ivy wrapping. But what I would now want to just make a point about is that we've tested Perceiver.io on an image, and actually the way that we design this is so that we can load in DeepMind's weights that are from their own repository. We kind of made sure that we implemented it exactly such that those weights are loaded in and give identical ImageNet results. And this is actually what we then see when we change the backend. So putting that to the top and looking at each of the various backends that we set when running inference on the Ivy Perceiver module, we see that we get almost identical prediction percentages for the top 5 predictions, basically. So all of them know with 87.36% that it's a Dalmatian. It might just be that one of them is 87.3615 and one is 10. So kind of the actual final predictions are off by a fraction of a percentage. And this is kind of right the way down through all of the kind of probabilities on I think it's 100 different classes. So the main point here being that even when we have different backends which have very different compilers, we also did with this with NumPy. I didn't actually get it added to the slide, unfortunately, but also it gives the same. So basically, even when you have a very, very deep network, errors don't seem to propagate for kind of for neural networks. It could easily be the case without testing. And this is obviously just one example, but we've tested this with others as well, and this is very much what we observe. So it could be the case that you might imagine that because of these small differences and you go through very, very deep networks, that these end up propagating and you end up getting different results. But yeah, this isn't what we observe, which is nice. Okay, so that's kind of Ivy as a framework in a nutshell. So now I'll go on to Ivy as a transpiler, which I think is where Ivy will see the biggest impact when we kind of got this all ready. Also, let me quickly just have a drink again. Also, I'll quickly again check if there's any questions, but don't think so. Okay, well, I'll crack on then. So where are we? Okay. So yeah, so to kind of just show on a high level what the transpiler does, it's useful to kind of quickly see the function signature. So basically this kind of simpler version of the transpiler, let's start with just thinking about transpiling a function and doing it eagerly such that we transpile it immediately. So we have the function to transpile, the framework to transpile to, the arguments for function tracing, and also the keyword arguments for function tracing. So what basically we do, we have these kind of 4 steps basically. We first need to compile the graph for the function that we're trying to transpile, and we compile it in the framework that the function is in. So if, for example, this was a JAX function, then we would get a JAX graph. We then replace each of these nodes with each node in this graph with the corresponding Ivy front-end function. This is the next step. We then convert the arguments to make sure that these are now, all of the arrays in the arguments and keyword arguments are also converted to the new framework. So in this case, these args and keyword arguments would be JAX arrays inside them, and we make sure then that they are now torch tensors, ready for the next tracing step. And then finally, we do another graph compilation step where we take this now Ivy code, because effectively it was a JAX graph. Now it's an Ivy graph with JAX front-end functions at the nodes, which then defer to Ivy functions. And then we do another function tracing to unwrap all of that and just get the kind of torch graph in this case, which again is then an optimized graph with no wrapping code around it. So to kind of flesh this out with an example, let's say we have some JAX function. I don't know why you would do this, but let's say it's a stacked Gelu function that we want to transpile to torch. And again, of course, this is very simple, but it just kind of emphasizes how this is done. So the first thing is to explain what these all would be in this case. So the function is stacked Gelu. Let's say we want to transpile to torch, and we pass in an array like this. We give a prox true and one iteration. So this is kind of what we're dealing with. And again, the first step is to compile this graph. That's the first thing we want to do. So the first point to make is that at this point in time, the compiler and therefore the transpiler only operate with static graphs. So whereas kind of PyTorch leverages dynamic control flow at this point in time, although it's something that we have plans to add support for, but at this point in time, the graph will be evaluated statically. So this for loop kind of is cached away and it's treated as constant. Likewise, anything is part of this graph that is not an array is also treated as constant. So effectively, these are treated as fixed. And what we get is this very simple graph where we take an x, we apply JAX Gelu, and we get the return, and then we have this shown in orange to demonstrate that this is a constant in the graph. It's not actually a variable, and actually we then can remove these visually because it's kind of just part of this function, basically. It's kind of baked into this function. So that's the first step. We compile the graph. Okay, so then the next thing we do is we replace each of the nodes in the graph with the corresponding front-end function. So in that case, very simple, we take JAX NN Gelu and we put ivy.frontends.jax NN Gelu instead. So it kind of is now, it's now an Ivy graph, but kind of by directly replacing the corresponding front-end function. Okay, so then we basically convert the arrays. So before this was a JAX array, we needed to pass this into the compile graph function because we do function tracing and we need to kind of see where the arrays go in order to connect the graph together. We now basically need to convert these to torch because we need to do function tracing a second time with the second graph compilation call. So that's that. And then basically what we do now is compile the graph again, and this complex graph emerges from the fact that on the version of torch that we're pinned to, the torch Gelu function doesn't support approximate as an argument. It does now with the latest version, but at the time of kind of creating this, then it didn't. So it still serves as a very helpful example of kind of what might sometimes be necessary because of some differences with the frameworks. And to explain why we have this quite complicated graph emerging, it's useful to take a quick look at kind of how this is implemented. So the JAX front end for Gelu simply wraps Ivy Gelu. So let's now take a look at this. So Ivy Gelu in Ivy activations. def galu. So oh yeah, well of course this is, sorry, just then choosing the backend. It's not compositional. It's a primary function, which means that each backend has a unique implementation. So now when we look at Torch's backend and we do here, we can see that because of the version that was the latest at the point that this was implemented, the approximate wasn't supported, and therefore we need to manually kind of hard code the approximate version of Gelu. And this is then basically where this graph comes from, because we did hard code the approx equals true. And again, we kind of can remove the constants because these are not part of the dynamic graph. They're kind of just baked in and are unchanging. So we can kind of just assume them to be part of this function, basically. And then this is the process. So it's a simple example, but I think that hopefully helps to kind of show what the transpilation is doing and how it's working under the hood. And now we kind of understand the basics of what's going on. We can then look at some examples of what this makes possible and what the transpiler enables. So, well, the first point to quickly make is that while we were considering this kind of specific function that's actually hypothetical just for the purpose of demonstration, which is transpile function eagerly, in reality we want Ivy's transpiler API to be much more flexible, so we enable arbitrary objects which themselves can be functions, models, kind of trainable modules, or Python modules. It can be any of these and also any number of these. And then also the two args and keyword arguments are all optional, and this is because we have these three different ways that we want the transpiler to be able to be used. So we want it to be possible to transpile either functions, trainable models, or importable Python modules. So you can kind of do any of these, not just individual functions. Also, any combination of these can be transpiled. If no objects are provided, then the function returns a new transpilation function which receives only one object as input. Basically, this means that we can use this as a function decorator, as we will explain in the following sections. And finally, if neither args nor keyword arguments are provided, then the transpilation will occur lazily, which will happen upon the first call of the transpiled function. Otherwise, transpilation is eager, and it happens during the transpile call, as it did here. But if we don't provide the arguments and keyword arguments, which are needed for function tracing, then instead the transpilation will happen the first time we try to execute the transpiled function. So now we can look at what that actually means for some examples. So let's first look at transpiling individual functions. So we're going to use Cornea as an example. For those who don't know, Cornea is a really useful computer vision library built on top of PyTorch, and yeah, definitely worth checking out. So we're going to look at a simple example. So let's kind of load an image into JAX, like so. The image in this case is ODSC. Then we can transpile this function. We can do it lazily because we haven't provided args or keyword arguments. We've just provided the function and the framework to transpile to. So now what we've got here, sorry, just to explain, is that we have this PyTorch only library. We have this edge detection function, and we now want it to become a JAX edge detection function. But we don't give the argument, so we can't function trace yet. But what we can do is then call the function on our JAX array. This will be quite slow because it will be doing the transpilation on the first run lazily, and we'll get the edges like this, which are actually generated from this demo. There was wasn't able to do it live, unfortunately, but we'll have the Jupyter notebooks up very shortly, so stay tuned for those. And then what we get here is, again, it runs fast, and it does so because it's already been transpiled, basically. And again, this is kind of how you can transpile an individual function from a library. And again, if we wanted to do this eagerly, it would just be as simple as this. So all we would do, you can see here it's lazy at the moment. All we do is add the arguments here to this function, which means we can actually do the function tracing. We can then transpile it, and both of these would happen fast. Okay, so now let's look at a TensorFlow example. We'll stick with Cornea, but now we'll transpile from PyTorch to TensorFlow. Again, let's load the image in, ODSC. But this time, let's say that we want to transpile not a standalone function that exists in the library, but let's say we want to transpile a composite function that we've defined that does something different. Of course, we could transpile the individual functions, cornea canny and cornea dilation, then just create the function. But what we can also do is create this composite function, which is actually in torch. It's also a torch function. And we can transpile this entire composite function to TensorFlow using a decorator like this. And yeah, again, so the reason that this is, the reason it's possible with the decorator here is that we're not actually providing the function to be defined in the first call. So remember here that we have the signature, so back a bit, but we have this signature here, objects with a star. This means we can provide none, and that works. So this is the case where transpile actually only receives 2, but then what it will return is a new function which itself consumes a single object or a collection of objects and then transpiles those. So that's what's happening here, basically. Also a bit of a lesson on decorators, that basically this calls the function, and then what is returned from this is what receives this function in the input. So this is how we can do it there. Again, no arguments were provided, so we don't do function tracing, so it happens lazily, which means that it's slow on the first call, then fast on the second call. If we wanted to do it eagerly transpiling, we could just pass the arguments here, it would transpile directly, and then these would both be fast. Again, just kind of a user choice really, as is also with regards to when the arguments are available. It might be that you don't know at transpile time what you actually need to pass in, and you only know upon the first invocation. So the lazy one is certainly more kind of user-friendly in a lot of cases. Okay, so that's how we can transpile individual functions. But of course, if you are using a third-party library, you don't want to have to transpile every single function you use, and this is why we also make it possible to transpile entire libraries. In this case, it's always done lazily because the idea of passing every single argument to every function you would ever want to call is not realistic. So basically what would happen is that every function you call then does the tracing and does the transpilation lazily, but I'll show you with an example. So for example, let's say we want to transpile the whole of cornea. What we can do is write something like this: cornea equals ivy.transpile cornea to TensorFlow. And what this will do is it won't actually transpile anything yet, but it will kind of prime the whole module to be ready to transpile anything as and when it's called. So what we can then do is, again, because we're doing TensorFlow, we load the TensorFlow image in. We can then define the same composite function, but we don't need to decorate it because we've now kind of TensorFlow-ified the whole of cornea. So we can now just treat it as a cornea library. We can actually pass TF1s here instead of torch ones because now dilation will be transpiled upon the first call. And again, because it's lazy, both of these canny and dilation will both transpile lazily on the first invocation, but then on the second one they will transpile quickly. And we won't need, and there's no way, at least with the current design, there isn't a way for us to transpile an entire module eagerly based on the current function tracing design. But this is something that, of course, you could hard code if you wanted to transpile eagerly. Yeah. Anyway, so this is kind of how you can transpile entire modules, entire libraries. So now we can talk a bit about transpiling models as well. So let's kind of assume, yeah, we've loaded in Perceiver.io from DeepMind's repository on GitHub, and it's a DeepMind Haiku module, and we have kind of a torch data set and the loss function we've imported, and we want to basically transpile this to torch. It is as simple as this. We can just call ivy.transpile Perceiver.io to torch nn module, and then what we get returned is a torch nn module. And then we can just train this in torch as with any other torch module. So we define an optimizer, we can then train it, kind of using this data set and this loss function that we've kind of assumed exist and train it like so. So it's worth looking at this a bit more, and actually we could dive into this a lot deeper, but I think for the purpose of kind of the time that there is today and everything, that isn't worth going into crazily into a lot of technical detail. But what I can say is that when we do this, we're basically doing two steps, which is we're first of all going to an Ivy module, and what we do here is that we basically take the Haiku module and we wrap this into an Ivy module, and we also transpile it to Ivy. So we kind of we take this JAX Haiku module, we then look at the forward pass, we do a graph compilation, we see what the JAX graph looks like, and then we replace that JAX graph with the JAX front end at each node, and then we kind of evaluate the Ivy functions that are composing each of these JAX front end functions, and then we're left with a pure Ivy graph. So the first step is to get this into an intermediate representation where we have an Ivy module that can be set, which can be run with any backend. When we then do to torch module, basically we first compile the Ivy module to a torch backend, again, so we kind of unwrap all of the Ivy wrapping code from the forward pass, leaving only the torch graph, and then we kind of thinly wrap this around the torch module interface. So we define all of the torch parameters explicitly by kind of wrapping them in torch n and parameter. We define the forward pass and everything. So basically, when we transpile a module, the important point to make here is that we first convert it always we first convert it to a framework-agnostic Ivy module, and then we convert the Ivy module to a framework-specific module class. And we need to make sure that we do this not just kind of transpiling the standalone front-end forward pass, but actually making sure that the trainable variables are correctly detected, passed to the right place, and everything. So there's a bit more going on here than there is just in the standard transpiling a kind of standalone function, where you don't really care about the difference between kind of trainable variables and so on. And also, just to explain on a high level, when we compile the forward pass of a module, we do so in such a way that the trainable variables are passed as inputs to the compiled graph. So we make sure that the module is responsible for keeping track of the variables, and the compiled graph remains effectively fully functional, and just kind of takes whatever comes in, including the weights, and does whatever computation is dictated by the graph. Okay, and then I think, so what we can now, what I think is worth discussing now is the fact that we have explored again with Perceiver.io and actually transpiled the JAX Haiku module into modules for each of these frameworks, effectively by doing this. So you can kind of imagine this translation process as first getting the Haiku module from Perceiver from DeepMind repository, getting an Ivy module, and then just kind of instantiating Torch, Keras, and reinstantiating a Haiku module from this intermediate Ivy module. And what we've then been able to do is look at the functional makeup of each of these graphs and kind of see how things have changed and how well replicated each of these modules are to the original. So yeah, basically what this graph is showing is the functions which are within the primary kind of low-level functions which are constituting the model, basically. So the original unmodified Perceiver.io from the DeepMind repository in Haiku has this makeup of JAX functions. As you can see, there's only 14 functions, which together have 2,049 instances. This is generally the case with most or many very large networks. It's very rarely the case, at least with us exploring kind of ResNet and Stable Diffusion and transformers and a lot of kind of big state-of-the-art models. They generally defer to a relatively small number of constituent functions. So this is the makeup of Perceiver.io. So when we transpile this to Ivy, so we kind of get it to the Ivy intermediate representation, we end up with 15 functions and 100 extra instances. And this is actually from a very simple reason, because at the time of recording, Ivy does not support reciprocal square root. If it did, this would actually be an exact kind of one-to-one mapping in this case. But because it doesn't, we have to split these 100 functions into, each of them needs to become 2, and therefore we get 100 extra instances and an extra function. Then, of course, when transpiling back to JAX from the Ivy intermediate representation, we have the same thing, because without some pruning step, without some kind of op fusion approach, which we actually are working on, but without that, with the kind of naive one-to-many transpilation approach, then we can't kind of combine reciprocal and square root back into R square root, because each of these Ivy functions kind of defines its JAX function, and there's no kind of inherent process to stitch these back together. So we end up with kind of the same 15 and 2149 instances. With TensorFlow, we have the same but one less function. Again, a small difference, but basically, again, we have the same R square root and splitting into reciprocal and square root, but also the expand dims is actually implemented using the reshape operation in TensorFlow. So ivy.expand dims with TensorFlow uses reshape. So this is kind of why we have this slight difference here. And then with Torch, again, more significantly, we have the reciprocal square root thing, but also, as we discussed before, we also have the reciprocal square root thing, we have the reshape thing as well, same as TensorFlow, and more significantly, we also, as discussed before, have the fact that GELU with an approximate equals true, which is what it is specified as in JAX, with the Torch version we're testing with, does not have the argument, and therefore we need to use this quite large graph that we explored not too long ago to have this quite heavy composition every time we call GELU, in order to make sure that we're using the approximate version and not the true version. So this is then kind of where we get a few extra functions here. With the latest version of Torch, this wouldn't be the case, and we can actually have GELU directly with true past, and it would be the same. And likewise, the introduction of R square root into Ivy would also alleviate that problem. In that case, with those changes made, which is certainly what's going to happen as we evolve into the next version, then there would be no overhead actually. We would have a kind of direct mapping, which is not in general always the case, but in this case, with a very large complex model, we do pretty much have a one-to-one mapping with the functions with these small differences addressed. But until that point, we have these small introductions of functions. But what I would emphasize here is that these are the kind of percentage increases for the number of instances of functions, but operations such as element-wise reciprocal and element-wise square root, kind of calling both of these instead of R square root is not going to add a 5% increase in runtime. And we're kind of in the process of crunching the full numbers for all of these on GPUs to see what the runtime overhead is. Most interesting would be the JAX one because it's the same framework, so we can kind of quite objectively only compare the runtime overhead introduced by the IR bottleneck. But all of the experiments we've done so far kind of are significantly less than 1% overhead for just these kind of extra ops here and there. Really kind of a very small overhead introduced by Ivy during transpilation. And with a bit of simple fusion, we already have a very simple op reduction where we take many ops, fuse them into one using some heuristics. We could potentially learn this using graph neural networks and stuff at some point. But with some simple heuristics, we can also kind of get this down a lot, and we get the exact number of instances in JAX and also TensorFlow. And importantly, as was the case before, when we run all of these on our very pretty Dalmatian, again, we get identical predictions. So these models are exactly the same model. Again, important to emphasize that this is with the pre-trained weights from the JAX model. So this is a network that was trained using Haiku, using JAX, which are now being used and converted to TensorFlow arrays or Torch tensors and being passed through a Torch module and getting exactly the same predictions. So this is kind of very strong verification that the model is functionally identical to the original, without us needing to kind of painstakingly implement it from scratch, just trying to recreate it. This is kind of an automated creation of a torch module, which is exactly the same as the original. Also, the transpilation process has numeric unit testing included, so even without needing to explicitly run an image through these networks, we verify during transpile time and compile time that they are identical by kind of step-by-step numeric unit testing. Okay, so that's kind of all of the points regarding Ivy as a transpiler. So all these different things that are possible. And what I would say is that, well, unfortunately, my desktop broke this week, so I haven't quite, I was hoping that this would all be fully live demo. What I can say is that the Jupyter notebooks for all of these are coming out very soon. I wasn't able to get them quite wrapped up in time for the conference, but stay tuned on the Twitter, because all of these demos that I've kind of screenshotted, gone through, will be there to play around with in a live interactive session in the coming days and weeks. So the next point is this kind of high level point really, which is that Ivy, well, I'll go to the slide first. So Ivy deliberately doesn't go particularly low level. It kind of stays at the realm of the functional API, the API at the array processing level, so kind of the API that we're all familiar with, that exists in TensorFlow and Torch and NumPy, etc., and trying to unify and create an intermediate representation at this level brings a lot of advantages, and not going lower brings advantages. One of which is that we don't lock ourselves into any low-level hardware or compilers or optimizers. So XLA, for example, is obviously amazing and a great compiler, and we could kind of start to try to bind explicitly around that. But kind of an idea that we're believing in and following is I suppose that the mathematics are kind of more fundamental, and this is something that is very future-proof, more so than anything else. So kind of designing around the kind of functional API of the mathematical operations keeps us very kind of agnostic to anything hardware or software related as much as possible, even to the extent that our intention is to step outside of Python at some point as well, and actually operate at an intermediate array API representation where everything that Ivy is today is just the Python backend of Ivy, and we could perhaps have a Julia backend and a Haskell backend or something. And of course, there are differences in how these languages work as well that are non-trivial to address, but kind of by enabling an intermediate representation that can connect APIs, which may or may not have open or closed source backends, for example, makes for a very future-proofed and potentially strong kind of central docking station, which anything underneath can plug into and connect to quite easily. So in a way, if we can now connect strong bindings so that anybody can transpile between all of these existing frameworks, all any new compiler designer or hardware designer would need to do is expose 100 or so functions to this kind of API representation, and suddenly this hardware and compiler can be run on from any of the frameworks that Ivy connects to. So kind of creating this centralized docking station, which I've said a few times now, is definitely one thing that we're very interested in, and trying to just connect all corners of ML in and outside of Python in the long term. Yeah, so this is kind of a bit kind of future directions, kind of where Ivy might be able to go in the realm of all of the kind of fragmented machine learning that exists. Yeah, so this is something that again is a little bit more just on kind of what's possible if we do have this intermediate representation, which many frameworks and many framework versions can very quickly transpile to and can enter this intermediate representation. We can build lots of things on top of that intermediate representation once, which then can be used by everybody. So for example, I mean, what we have now is this trace operation, which is the graph compiling, basically converting to Ivy, kind of transpiling to Ivy. You could say it's unifying. Specifying is transpiling from Ivy to a specific backend. simplifying kind of the pruning we talked about, where we do operation fusion, for example, adding reciprocal and square root into R square root, and also more complex ones as well, where we can find kind of parts of the graph that can be fused into a single operation, perhaps using graph-based learning. Tensorization, so Tensorly is a great framework, and generally kind of treating neural networks as high-dimensional tensors and doing tensor decomposition is a very good way to compress networks. So this is also something that could be done in Ivy space and kind of implemented and tuned once, and can be applied to any framework that can be transpiled to Ivy. And then, of course, like generating source code is something that would be very interesting. At the moment, everything is a kind of black box computation graph that is not incredibly simple to modify afterwards, and actually being able to generate human readable source code in the target framework is something that we think is possible and that we're working on as well. And of course, then compiling to low-level hardware, and then kind of you can compose these to do lots of things. So transpiling for inference by compiling directly to the hardware, maybe transpiling then Pythonizing to actually generate source code, so you can kind of you can take perceiver IO, you can generate human readable source code in TensorFlow and use that as a starting point to then do your own modifications. That would be very useful, beyond just having kind of the graph there. So there's lots of things that can be built upon Ivy's intermediate representation, and Ivy is a framework, which we find very exciting, but definitely kind of getting the transpiler working broadly so that everything is connected is kind of really step one. And then finally, before going to questions, I know we've got kind of 20 minutes or so left on the clock, and I'd like to leave enough time for questions. The last thing I want to say is just a thank you to everybody that has contributed a lot to Ivy. I mean, actually, there's way too many people to mention with us now having over 500 contributors. So every contributor has helped towards getting Ivy where it is today. So certainly all of them deserve a thank you. But I've got a slightly smaller list of people that I want to thank who've been like more actively involved in the project. So all of the people here have contributed a lot to Ivy. So although it's me presenting at the moment, it's not me doing the work or doing all the work at all. Far from it. So everybody here is as much behind this talk and the work as I am. And also special thank you to some people that helped getting the results ready so some of the results I presented today and getting some prep done for the talk. I want to make a special thanks to these 9 people as well. And in general, we are hiring. So anybody also that's interested, kind of either listening live or maybe watching the recording, please reach out on the website and take a look at the bottom, and very interested for people to get involved. We're also, beyond that, always open for open source contributions. So we try to make our documentation as kind of user-friendly as possible, so that there's always things to do. Our Discord server is always very welcoming to people who want to get involved. So if you kind of like the story that you've heard and you think it's kind of has a shot at working, then we would love for you to get involved and just come join the Discord, ask some questions, make a few PRs and stuff. Everybody's very welcome. Cool. So we've finished. I kind of finished a bit earlier than I thought, but there's now a good kind of 15 minutes or so if there are any questions. Okay. So I see there's one already. So I see Vinod has a question, which is, after the target graph is generated, are there any optimizations done on top of it, i.e. the target module may have a simple function that can replace an entire subgraph? So that's a great question. I'll answer live, basically. So yes, it's something we're working on. So at the moment, it's in an early process, as we kind of showed on one of the slides before. We kind of do very simple passes, which is kind of finding redundant as array functions which appear every now and then where it is an array, and we call as array, and we can remove that. Sometimes because of kind of quite careful typecasting in Ivy functions to make sure that we're always doing things correctly, we end up calling a kind of to data type on an array that is already that data type. And like really simple things like that, we do have a pruning step in place where we can remove those from the graph, because of course they're just adding redundancy. But for the more kind of sophisticated many-to-one operation simplifications. It's not something we do yet. The first thing to do, which will be quite simple, would be to basically use our API as kind of a dictionary. So we can kind of find all of the subgraphs in the tensor in the PyTorch backend, let's say. So when we look at all of the Ivy API and we look at each Ivy function and we look at all of the ones that include multiple torch functions in the backend, this is very likely to be a subgraph that might appear when we're kind of transpiling to torch or something. And so therefore we can do a simple dictionary lookup there to find. But of course, like finding subgraphs in a graph is a hugely complex problem, and there's like a huge number of subgraphs in a graph. So this is something that we think long-term with graph-based learning and kind of maybe even an RL loop to kind of tell us when it's being done right and wrong could be interesting. But that's definitely future work. Yeah, but we're trying to kind of get the good heuristics and the hand-engineered stuff done as well as we can to make sure we fix any kind of common inefficiencies that are introduced in this manner. Yeah. Okay, hopefully that was a. If you have a follow-on question, very welcome to ask one. Any other questions at all? It's also very possible that I went through slightly quickly. I do have a slight tendency to talk relatively fast. The other thing, yeah, another great question. So yeah, that is it's something that again is on the radar and is something that I think would be very useful. If we do explore that, then of course we would want to look more deeply at the way that ONNX has done things, because of course they are a kind of exchange file format, and maybe we don't need to kind of reinvent wheels there. So perhaps we could extend that with other functions that Ivy supports, etc. Yeah, it's definitely something that we want to do and explore. But at the moment, no, it's kind of, at the moment it is basically all just in memory. We can save the graph. It would effectively be just some kind of file representation of Ivy's API, because Ivy's functional API is the intermediate representation. So in that sense, maybe it wouldn't be possible, and it would kind of necessarily be a bit different to the ONNX version, although we could certainly have it as we could certainly convert to and from it. Sorry, I'm going on a few different directions, but yeah, yeah, thanks for the clarification. So yeah, I'm actually, to be completely honest, I'm not familiar with PMML actually. Probably something I should be, quite possibly. So I'll look into that. But definitely, yeah, I definitely think that's something that would be very useful. But I think if we did, it would effectively be okay. Yeah, thanks for clarifying. Okay, so I should also, just because I'm recording this as well, and I'll quickly read out loud the questions. So yeah, just to quickly, for anybody that's listening, perhaps on a non-live version, then yeah, Vinod asked, have we tried exporting? Have we considered exporting to intermediate graph into a format that can be read into another tool, and it can maybe be yeah, the graph could work as an intermediate exchange format, for example, motivated by specs like predictive modeling markup language, which is the XML-based spec. Yeah, hopefully that was a somewhat concrete answer, but still quite early on that front. Okay, any other questions at all? I think these are all done. One thing I will add just in the meantime, because otherwise we could finish early, of course, no need to use the full time. One thing that I will add is that, which I think I mentioned already, but there will be Jupyter notebooks for all of these kind of screenshot demos in the coming weeks. Yeah, which people then will be able to try out themselves, which I think might kind of lead to more questions as well, of course. Okay, I'll just wait a few more moments. Otherwise, I think we can perhaps close. Okay, well, I'll assume that that was all clear. Yeah, not quite as many live demos as had originally planned, but these won't be too far away. So definitely stay tuned for these sometime in November. And yeah, thank you very much for listening, everybody. Really an honor to talk at this conference, and really great to have so many people in the audience. And yeah, hope everybody has a great rest of the conference. Thanks a lot.